Hi, folks. Today we're going to learn about strong versus weak acids and bases. And the first thing you need to know is that this is a different concept to concentrated versus dilute solutions. When we say the words concentrated dilute, we're describing molarity, how many moles you have dissolved in 1 liter of solution. If you have a concentrated solution, you've got many moles dissolved in 1 liter of solution. If you've got a dilute solution, you have just a few moles dissolved in 1 liter of solution. On the other hand, strong and weak describe how well acids and bases ionize, how well they split into their ions when dissolved. What makes an acid or base strong is that they fully ionize. So a strong acid fully ionizes. It separates into its hydrogen ions because all acids have hydrogens, and some negative ion to balance that charge. Similarly, strong bases fully ionize. And typically, a base, what makes a base is that it has hydroxide ions or produces hydroxide ions when it dissolves in water. Um, Weak acids and weak bases, on the other hand, do not fully ionize. So some molecules are going to stay intact, whereas others will ionize. So there are 3 acids that are considered strong acids. Those are hydrochloric acid, nitric acid, and sulfuric acid. And so you can see here that these are fully ionized in water, these 3 strong acids. And then as you move down this list, these acids become less and less ionized in water. There are 4 strong bases. And those are lithium hydroxide, sodium hydroxide, potassium hydroxide, and barium hydroxide. And so if you have hydroxide ions that are not in that list, if you have bases that are not on that list of 4, then they are considered weak bases. Now, just because something's considered weak, not all weak bases, not all weak acids are the same. There are some that are stronger than others. It is a spectrum. Um, and but for the purposes of Chem1, knowing what 3 strong acids and 4 strong bases there are is important. So pH is a measure of the concentration of hydrogen ions that an acid or base creates in a solution, any substance creates in solution. So we use square brackets to indicate concentration. So this symbol here represents the concentration of hydrogen ions. But hydrogen ions are protons, and that's too reactive to really exist on its own. So hydrogen ions don't really exist on their own. They attach themselves in solution to water molecules to create the hydronium ion, which is H3O with a +1 charge. So these are kind of interchangeable. They're kind of getting at the same idea, the concentration of hydrogen ions or the concentration of hydronium ions, because really those hydrogen ions aren't really existing on their own. They're attaching themselves to water molecules. And so different sources will refer to this concentration in one way or the other. The formula for calculating pH is pH equals the negative logarithm of hydronium ions or hydrogen ions in the solution. And that negative log function is something that we'll practice on our calculators in class. But with that negative log, what you get is a low pH means a high concentration of hydrogen ions. So acids have low pH. Just to clarify, that square bracket notation just indicates concentration. So we're referring to what is the molarity of, we're using the molarity of hydrogen ions or hydronium ions. So that concentration of hydrogen ions or hydronium ions depends on a few things. First, it depends on the acid concentration. Do you have 1 molar hydrochloric acid, 2 molar hydrochloric acid, 6 molar hydrochloric acid? It depends on the strength of the acid. If you have 1 molar of hydrochloric acid, it fully dissociates because it's a strong acid. And so the hydrogen ion concentration is high. Whereas if you have a weak acid, like um, uh, hydroiodic acid, then that does not fully dissociate. So even if it's 1 molar, both solutions were 1 molar, there's going to be a higher concentration of hydrogen ions in the hydrochloric acid than the hydroiodic acid. The other thing it depends on is the formula of the acid itself. Some acids have more than one hydrogen ion that they can release, more than one acidic hydrogen ion. Um, so sulfuric acid, for example, has 2 hydrogen ions that it can give up, whereas hydrochloric acid only has 1 hydrogen ion. So these are all factors that play into that hydrogen ion concentration. So let's look at some examples here. If we have uh, 0.03 molar hydrochloric acid, this is a strong acid, so it is going to fully dissociate in water. And so this is fully going to break into the hydrogen ions, positive hydrogen ions and negative chloride ions in a 1-to-1 ratio. So there's going to be 1 hydrogen ion for every 1 molecule of hydrogen chloride that you start with. So what this means is that we end up with the same quantity or the same concentration of hydrogen ions that as we had for the original concentration. So we started with 0.03 molar hydrochloric acid, so we have 0.03 molar of hydrogen ions or hydronium ions. Now, if we look at another strong acid, like sulfuric acid, but this acid has 2 hydrogens that it can release in solution when it's dissolved in water. So this has a 2-to-1 ion ratio. That means that when we start with 0.03 molar sulfuric acid, we actually end up with twice that concentration of hydrogen ions. We end with 0.06 molar hydrogen ions or hydronium ions. Now, with the sulfate ion, we still have 0.03 molar of that because there weren't 2 sulfate ions per molecule. There was just 1. Now, the hydrogen ion concentration of phosphoric acid. Phosphoric acid is a weak acid, so it does not fully dissociate in water. So even though it looks like I should have a triple concentration of hydrogen ions, you don't actually achieve that. That's what you would have if it fully dissociated, but it does not fully dissociate. Uh, and in reality, what you have is a concentration of about 0.011 molar hydrogen ions, hydronium ions. So this here is evidence, but when we measure the concentration of hydrogen ions, we see that we don't have the expected 0.09 molar concentration of hydrogen ions. Therefore, we know that this acid did not fully dissociate. Therefore, we can categorize phosphoric acid as not a strong acid. We can do similar calculations or with bases to kind of figure out how the relationship of the hydroxide ion concentration relates to the original concentration of the base. In terms of visualizing what's happening here between weak versus strong, concentrated versus dilute. In this picture, the red and white particles are representing water, so 1 red oxygen, 2 white hydrogens in those molecules. And then in each picture, you can see a hydronium ion. So both of these pictures represent an acid. because they make H3O plus, those hydronium ions, when dissolved in water. So we've produced hydronium ions. These are both acids. Now, look at these uh, particles here. A is whatever the acid is, we're going to call it acid A, um, or in picture A. A is concentrated because there are so many solute particles dissolved in water. Remember, concentrated versus dilute refers to how many moles of solute you have dissolved in a certain volume of solution. So, picture A is concentrated because there are so many solute particles dissolved in water. But if you look at those solute particles, the four that are circled in green still have their hydrogen attached. Only the one acid particle that's circled in blue has actually lost its hydrogen. Therefore, acid A, the solution A, represents a weak acid because some of those solute particles, all the ones circled in green, do not ionize in water, do not separate into the blue part and lose the white hydrogen ion. If we look at substance B only has one acid particle dissolved in that same volume of liquid. Therefore, B must be dilute. There are few particles dissolved in the water. However, every particle there, and yes, there's only one of them, every particle there has lost its hydrogen ion. Therefore, represents a strong acid because all of those solute particles fully ionized in water. So this is kind of a picture representation of what is the difference between strong and weak. What's the difference between concentrated and dilute? Now, with these two solutions, even though we have a strong acid that is very dilute, that's what picture B represents, and we have a weak acid that's more concentrated, that's what picture A represents, the pH of these two solutions are equal because they have the same number of hydronium ions per volume of water. So each just produced one hydronium ion in this particular volume that you see presented here. So here are various formulas to help you calculate pH. If you know the concentration of hydrogen ions or hydronium ions, you just use the standard pH equation here. If you know the pH, but you want to know what is the concentration of hydrogen ions, you use the reverse of this equation. You kind of solve for the concentration of hydrogen ions, and the inverse operation of a logarithm is raising 10 to that exponent. POH. POH is something that perhaps you haven't heard of before. Most people have heard of pH, but they haven't heard of POH. POH is a measure of the concentration of hydroxide ions. And the relationship between POH and pH is that they always add up to 14. It is sometimes easier to measure the concentration of hydroxide ions than it is to measure the concentration of hydrogen ions. So it's useful to be able to switch back and forth between the two. So to calculate the POH, you need to know the concentration of hydroxide ions, and you take the negative logarithm. Again, this equation can be reversed, much as the pH equation was reversed in equation B there. And as I said, POH plus pH always sums to 14. So you have not learned about logarithms yet. You learn about those in Algebra 2. So I have just kind of an overview of how to understand what logarithms are doing and kind of which buttons to push on your calculator. So To take the log of the number 100, the answer is 2. Why is the answer 2? Because 10 raised to the second power equals 100. That's what a logarithm is doing. It's kind of uh, taking an exponent into account. Similarly, if you take the log of 0.001, again, you should be trying these on your calculator and seeing how making sure you're getting the same answers that I'm showing you here. When you take that log, you should get the answer of -3. Why is that? Because 10 raised to the -3 power is 0.001. Log of 0.0001 is -4 because 10 raised to the -4 power is 0.0001. Now, everything we've done so far has been a power of 10. What if we take the log of something that is not a power of 10, 0.0005, for instance? This is clearly between the second example and the third example. So our answer should be between -3 and -4, but it's not halfway between -3 and -4. That's not how a logarithmic scale works. The value is -3.3 because 10 raised to the -3.3 power is approximately 0.0005. That's not the exact answer, but it's an approximation. So now that we have an idea of how logarithms work, let's do some practice problems. So the pH of 0.03 molar hydrochloric acid. What is the concentration of hydrogen ions in this example? Well, my concentration of hydrogen ions, because there's just one hydrogen ion that's going to be lost per hydrochloric acid molecule, hydrogen monochloride molecule. The hydrogen ion concentration is the same as this concentration listed here, 0.03 molar. Then, if I calculate the pH, I need to put this concentration in here. So I want to find the negative logarithm of 0.03. My eraser is not working. So we'll just deal with those scribbled in markers. So negative logarithm of 0.03 molar. And if you do that calculation, you get 1.52. Make sure you don't get the answer -1.52. You need to remember to have that negative sign out front. The log of 0.03 is a negative number, but taking the negative of a negative gives you a positive answer. Let's look at the next example. If I have a pH of 0.03 molar sulfuric acid, this is a strong acid. It's going to fully dissociate in water. But this time I'm going to have 2 hydrogen ions per molecule of sulfuric acid. So my hydrogen ion concentration is twice as strong as what I see listed here, twice of 0.03 molar. So I have 0.06 molar. And now if I replace this with 0.06 and take the negative log of 0.06, then I get as my answer 1.22. So you can see that even though hydrochloric acid and sulfuric acid, these both have the same concentrations, because there are more hydrogen ions in sulfuric acid, my pH is lower. My pH is lower because I have more hydrogen ions, a higher hydrogen ion concentration. In example 3, if I start with 0.03 molar H3PO4, this is not a strong acid. This is a weak acid. So I cannot just assume that that I have triple this amount of this concentration of hydrogen ions. And in fact, I need to work backwards. I'm given the pH. I need to work backwards to find out what the hydrogen ion concentration is. So for this equation, to calculate the hydrogen ion or the hydronium ion concentration, I need to take 10 and raise it to the negative pH power. So I need to take 10 and raise it to the negative 1.96. And if I do that, I get 0.01096 molar as my concentration. My concentration specifically of the hydronium ion. Another example, what is the pH of 0.5 molar barium hydroxide? This is a strong base. This is a strong base, so it fully ionizes in water. And you can see that for every 1 molecule of barium hydroxide or 1 formula unit of barium hydroxide, I'm going to get 2 hydroxide ions out of that. So even though my concentration of base here is 0.5 molar, I'm going to double that for my concentration of hydroxide ions. So I'm going to have 1 molar of hydroxide ions. Now, here in this example, I want to know the pH, but I have no idea what my concentration of hydrogen ions is. I know what my concentration of hydroxide ions is. This is where pOH is particularly helpful. I know that pOH is the negative logarithm of the concentration of hydroxide ions. So I'm going to plug in the number 1 here. And the negative logarithm of 1 is just 0. So my pOH is 0. But I know that pH plus pOH equals 14. So my mystery pH value plus 0 equals 14. And so if I solve this equation, then I know that the pH must be 14. So my pOH was very low, which means my pH is very high. And this is why bases have a high pH. I hope this helped.